application of statistical mechanics to thermodynamics is called statistical thermodynamics. Using this, we are able to calculate macroscopic properties like pressure, volume, temperature, entropy, etc. from a simple knowledge of how many molecules occupy different energy levels. To calculate the number of molecules occupying different energy level, we utilize these statistical principles for that. Before that, let me introduce some of the few terms which you should be familiar with. In a collection of particles, each particle is called a system. Number of particles joined together is called an assembly. Assemblies are independent of each other. Collection of these assemblies is called an ensemble. I said from a knowledge of how many particles are present at each energy level, we will be able to calculate the macroscopic properties like pressure, volume, temperature, entropy, etc. How to do that? There are three basic principles to calculate the number of particles at each energy level. They are Maxwell-Boltzmann statistics, Bose-Einstein statistics, and Fermi-Dirac statistics. Maxwell-Boltzmann statistics, Bose-Einstein statistics, and Fermi-Dirac statistics. These are the three statistical procedures to calculate the number of particles at each energy level. Once you have an idea about the number of particles at each energy level, it is possible to calculate all these thermodynamic properties of a macroscopic system. For each particle, you won't talk about pressure, volume, temperature, etc. Only for the collection of particles, you will talk about this. Let me tell you what this Maxwell-Boltzmann distribution law tells us and how to calculate the number of particles at energy levels. The first assumption made by the Maxwell-Boltzmann is that particles are distinguishable, which is not true. Let us say I have a gas with the number of particles, number of molecules. How can I distinguish one molecule from the other molecule? That is not possible. It assumes, based on this assumption, it makes a derivation. And there is no restriction on the number of particles at any energy level. Any number of particles can be present at an energy level. However, it says that total number of particles is constant and the total energy is constant. So let us derive an expression for the number of particles at any energy level. Let the total number of particles be n. Let n1 particles are at level E1. I said there is no restriction. Any number of particles can be present at any level. and let N2 particles are at level E2, so on and so forth. Generally, I can say Ni particles are present at level Ei. The total number of particles is a constant, I said, and the total energy is constant. The total number of particles, sigma Ni, is equal to N, which is a constant, which will not change. The total energy, sigma Ei Ni, is equal to E, which is also a constant. So now let us calculate what is the maximum possible distribution, what is the expression for maximum possible distribution, and how to calculate the number of particles at any energy level. The thermodynamic probability or maximum possible distribution is given by the symbol W. This is called thermodynamic probability. According to Maxwell Boltzmann, W equal to n factorial divided by n1 factorial, n2 factorial, etc. etc. This is the expression for the maximum thermodynamic probability. Now, let me take logarithm for this. So, ln W is equal to ln n factorial minus ln n1 factorial plus ln n2 factorial, etc. Or I can write this as ln n factorial minus sigma ln ni factorial. Whenever there is a factorial of a very large number, an approximation called Stirling's approximation is used. According to the Stirling's approximation, ln n factorial is given by n ln n minus n. This is the Stirling's approximation, provided n is a very large number. So I am going to apply the Stirling's approximation to this and write so introducing this into this equation, I can write it as ln W equal to, instead of ln n factorial, I will write as n ln n minus n minus sigma ni ln ni minus sigma ni. That is equal to n ln n minus n minus sigma ni ln ni plus n, because sigma ni equal to n. So ln W equal to, this is the maximum possible distribution, ln W equal to n ln n minus sigma ni ln ni. Since W is maximum, ln W is also maximum. So differential of ln W, since it is maximum, there can't be any further change. So d ln W will be equal to 0. So if I differentiate this, d ln W equal to, this is the n is a constant. So differential of this constant is 0. I need not write it. So differential of this I will write minus differential of this quantity. This is equal to 0. I can even write differential of n ln n minus differential of this. Since the n is a constant, differential of this is 0, so I have not written. So simply saying differential of this quantity is equal to 0. Differential of sigma ni ln ni is given is equal to the result. I am not doing the differentiation and all that. I will straight away give you the result. It is nothing but sigma 1 plus ln ni dni equal to 0. This is the differential of this. Since ln ni is large, one can be neglected, and I can simply write it as sigma ln ni dni equal to 0. So this is the condition for the Maxwell-Boltzmann distribution, where ni is the number of molecules at any energy level, dni is the change in number of molecules in that level. To this condition, two more conditions are added, namely sigma dni equal to 0, sigma ei dni is equal to 0. Meaning of this is, if number of molecules at one energy level decreases, a corresponding increase will be other level. So the total change will be equal to 0. Similarly, if number of molecules at one low energy is large, a corresponding decrease will be there in high energy. So these are the three conditions to be obeyed by the Maxwell-Boltzmann distribution law. Now, expanding it further, I am going to add these three. I am going to multiply these two by constants and add to this. This is condition 1, this is condition 2, this is condition 3. I am going to combine them. For that, I will multiply this by a constant alpha and multiply this by a constant beta and add to the equation 1. The result will be sigma ln ni dni plus alpha dni plus beta into ei dni is equal to 0. This is the condition according to the Maxwell-Boltzmann distribution law. Or I can write it as sigma ln ni plus alpha plus beta ei dni equal to 0. There can be change in the number of molecules at any energy level. As I told you, if there is a decrease of a number of molecules at one energy level, a corresponding increase will be there in the other energy level. Therefore, dni cannot be equal to 0. dni cannot be equal to 0. By dni I mean the change in number of molecules at any energy level. That can never be 0. Therefore, this must be 0. Namely, sigma ln ni plus alpha plus beta ei is equal to 0 is the condition according to the Maxwell-Boltzmann distribution law. Now, let me find out what are the values of the alpha, beta, etc. So, in a simple way, I can write it as ln ni plus alpha plus beta ei is equal to 0 is the law according to the Maxwell-Boltzmann. Or I can write as ln ni equal to minus alpha minus beta ei, or ni equal to e power minus alpha into e power minus beta ei. This is the expression for number of molecules at any energy level according to the Maxwell-Boltzmann distribution. Now let us evaluate what is the value of the alpha and what is the value of the beta. So evaluation of the constant, alpha and beta are arbitrary constants. So we are going to find out what is alpha and what is beta. We said Ni equal to e power minus alpha, e power minus beta Ea. This is the expression for Ni which we wrote. So now we are going to evaluate what is the value of this alpha and what is the value of this beta. So I can write sigma Ni equal to e power minus alpha sigma e power minus beta Ea, or sigma Ni is nothing but n. So n equal to e power minus alpha and sigma e power minus beta Ea, or e power minus alpha equal to n by sigma e power minus beta Ea. This is the expression for e power minus alpha. Inserting this value of e power minus alpha into this equation, I can write as Ni equal to n by sigma e power minus beta Ea into e power minus beta Ea. This is the expression for the number of particles at every energy level I, that is equal to n by sigma e power minus beta Ea into e power minus beta Ea. In the estimation of beta, we will write the Boltzmann equation as Ni equal to e power minus alpha e power minus beta Ea. We have already found that e power minus alpha is n by sigma e power minus beta Ea into e power minus beta Ea. A basic relation connecting the entropy and the probability is S equal to K ln W. This equation is also known as the Boltzmann equation. Entropy is directly related to the randomness. If W is large, that is, a distribution pattern is very large, entropy also will be large. So S is equal to K ln W, or S equal to K into, I introduce the expression for ln W here. So S is equal to K into n ln n minus sigma Ni ln Ni, or K ln n minus K into sigma Ni ln Ni. K ln n, sigma Ni is nothing but n, so Kn into, instead of ln Ni, I will use this expression Ni equal to e power minus alpha e power minus beta A. Therefore, ln Ni equal to minus alpha minus beta A. I introduce that here. Or that is equal to Kn ln n plus Kn alpha plus K beta E. This is the expression for the entropy obtained from the Boltzmann equation. We are going to evaluate beta. That's it. Now, let me find out what is dou S by dou E. That is, I am differentiating this with respect to E. This doesn't contain any E. This doesn't contain any E, so it will be 0. So it will be simply, it is going to be ds by d equal to k into beta. By definition, S equal to ds equal to q by t. That's the basic definition for the entropy change. According to first law, q is nothing but dE plus pdV. So ds equal to dE plus pdV by t. If the volume is constant, it is nothing but dou E by t. Dou E by t. Or dou S by dou E is equal to 1 by t. So k into beta is equal to 1 by t. Or beta equal to 1 by kt. So I have evaluated beta also. So I can write the complete Boltzmann equation. Introducing the value of beta, we get Ni equal to n into e power minus Ei by kt divided by sigma e power minus Ei by kt. Suppose at any level there is degeneracy. Just as I told you, among the p orbitals, px, py, pz, all the three are of same energy. So if the degeneracy is Gi, I write the equation as Ni equal to n into Gi into e power minus Ei by kt divided by Gi into sigma e power minus Ei by kt. This is the celebrated Maxwell-Boltzmann distribution law. The quantity Ga sigma e power minus Ei by kt is called partition function, a very important parameter. Using this partition function only, we are going to calculate all the thermodynamic parameters, denoted as F. So Ni is equal to n by F Gi e power minus Ei by kt is the Maxwell-Boltzmann distribution law.